All right. Welcome. This is now part 4 out of 5, 6, 7, right? For the Steady Flow Devices series, right? So this is very in depth, and I'm taking this very slowly so that, you guys don't get all confused, right? Now we are going to talk about turbines, or, turbines. Well, there's this whole discussion, right? We kind of don't know what the very correct pronunciation of this word is Turbine. A lot of people already say turbine, right? But turbine is actually, I don't know if this is true now that I think about it, right? It's the short form for the word turbo machine. So turbo machine, turbine. Right? A lot of people say turbine, or sorry, some people say turbine. My girlfriend says turbine, right? And well, technically, I guess, right? If that is true, it's turbo machine, not turbo machine. So there's no turbine. And then I tell her, like, oh, that's a pretentious way to say it. And she says, you should mind your own business. And so, well, whatever it is, right? However you want to say it. If you want to be a little fancy, you can say turbine, right? A lot of people say turbine. In Tagalog, turbine is turbina, right? And well, the Latin is also kind of supporting turbine, right? Turbinem, which means spinning top. But anyway, a turbine is just any device that converts energy from a fluid into rotational mechanical energy. And well, by extension, if you hook this up to a turbine, if you hook this up to a generator, you're going to create electricity, right? Create is a generate, maybe convert the fluid energy into, you know what, yeah, enough with the technicalities. You're going to generate electricity, right? The thing about this is that this is supposed to be isentropic, right? The fluid goes into the turbine so quickly, right, that it has no chance to transfer heat out or into the device, right? Turbines work the same way, kind of. Say, for example, right? The example that I gave in class was, if you were a kid, right, you made these okay, yeah, there you go, that's your kid. And then the kid is now blowing on the windmill. How did I this this then like this, like that, right? There you go. Sorry, I had a tough time trying to draw this windmill. So this windmill right here, the ones that you make out of paper, right? They operate the same way as the gigantic wind turbines in, like, I don't know, in Ilocos maybe, right? And these things work the same way. You have air flow through them, and because of the design of their blades, they will start spinning, right? If you get a kid or multiple kids to blow on this so fast, right, that it will generate electricity, then maybe that's free energy, but that is also child labor. So we just let air at high altitudes do it for us, right? That is the rationale for using wind turbines like these ones, right? But in this case, we are not talking about wind turbines. We are talking about steam turbines. We are talking about letting steam, which is very high, very powerful, right? Very high temperature, go inside these turbines. And because they are so high energy, they want to pass through this thing so quickly that they're going to spin the blades of the turbine. And that spinning causes the kind of energy that you're going to harvest. Okay? So that's the thing that we want to see in this example, right? Or in these examples, right? And well, technically, while this thing is uploading, or has it uploaded already? Oh, it has uploaded. So now you're seeing you're seeing the the inner workings of the channel. But steam turbine, right? Thing about this is that the steam turbine, yeah, you can see these things are gigantic. These are ginormous. Look at them, right? It's actually kind of scary now that I look at it. Open image in new tab. Oh boy, they're very scary. Let's look at maybe here. Does that is that better? Okay, it's not great. It's not big. You know what? We've seen enough. Oh my goodness, look at that. Oh, that is gigantic. Wow. Look at those things, right? Basically, what happens is that steam tries to go past this ginormous turbine, right? And because they're trying to go past this turbine, they will inevitably spin these blades, right? Some of these blades are stationary, some of them are moving. You'll learn more about them later down the line in fluid mechanics, fluid machineries. We'll talk about impulse turbines, right? You will talk about reaction turbines. You will talk about different kinds of turbines, all that jazz, right? And basically, that is what generates your electricity. Look at that shaft. It is humongous. Okay? I don't know how big a person is right here. There are no like identifying there are no identifying marks in here, but maybe just like looking at the background, I think that I may be as tall as where the shaft is, maybe. Okay? But this is still humongous. Okay? Now, anyway, right? Now we go back here to the turbine. Yeah. The thing now is that this turbine, you expect this to move. You expect this to rotate, which is where the work is going to come from. Right? But because this is ideally isentropic, there should be no heat transfer. This should be insulated. And most of the time, but not always, KE and PE are negligible, usually, most of the time. Okay? And so what we will see in here is just that your work, right? Negative work is equal to your delta H. You might say that there's a negative in there. Why is there a negative in there? Let's just see. Okay? Now, this is how a turbine is drawn in a schematic diagram. Now you notice, why is it a trapezoid? Well, it's a trapezoid because if you look at the back end of this thing, let's give it a little copy paste action, right? Actually, just get everything in here, delete, then maybe put in the gigantic turbine in here, right? Notice that at the back, right, you will have this here and then this here, right? Which, if you're going to look at from the side, is going to be this thing, right? It's going to be this thing. That is where the turbine comes from, okay? And so you might notice, okay, so what is this then, right? Is that just the turbine that's, that's facing itself? Well, it's hard to say from the looks of it, but it seems that this is a compressor, which is the next part pa. But yeah, this is what a turbine is supposed to look like. And yeah, there you go. Okay, we now go here. All right, so this is how a turbine looks like. Notice that what comes into the turbine should be very high energy fluid, right? Because this high energy fluid will try to go past the blades, will try to go past to go down to the lower or to the next state. What it will do is that it will pass the energy to the turbine blades. It will make the turbine blades spin. And that spinning is already some rotational kinetic energy, which again, if you hook it up to a generator, you will generate electricity. And so, as a result, it's passing energy to the blades. It's passing energy to the turbine. Oh, so that means it will lose energy after. And what the difference will be between H1 and H2 is the work that you generate. Notice that you can also think about this the same way you would think with the first law, or rather the language version of the first law. Whatever goes in, right? Your H1 is going in, must go out. What goes out is your work of turbine, and whatever goes out is your H2. Now notice, let's just look at the first law version first, the one that we were canceling in here. Let's try and let's move you out now. There you go. What you will see in here, Q minus W is equal to delta KE plus delta PE plus delta H. What you will see in here is cancel, 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 right? You will get negative W is equal to delta H, which if you remember is just going to be H2 minus H1, out minus in. Notice which state has more energy. Of course, it's going to be H1 because that has yet to give up its energy to the turbine. So that means that your H2 minus H1 is actually a negative value. Okay, so if it's a negative value, oh, that's why there is a negative sign in here, because in the end, right? In the end, this value of W is positive. How am I to say that it is positive? It's because your turbine work is going out. Work out is positive. That's how we're supposed to think about it, right? On the other hand, if you want to draw the schematic diagram, right? If you want to draw the schematic diagram, it's like this. This is the turbine. This is your state 1, which has, right, just state 1. And then your state 2 in here. You know that you're going to generate energy. I denote it in the sense of a lightning bolt. That is what my work is. So that is work of turbine. And now notice, whatever goes in, so that is H1 must come out, which is now H2. So whatever goes in, H1, has to come out. Work of turbine plus H2. Notice that what happens in here is you can just put this to the other side. You'll get WT is equal to, H1 minus H2, which is the same thing as in here. So both of them work. All right, now let's see them in action. Let's have problem 5.4. Oh, but before that, yes, you might see in the thumbnail of this video that this is actually called turbines and expansion engines. Their expansion engines are basically just parang umbrella terms, right? They're more general terms for turbines because what they do is not only generate work but also lower the pressure of your state, of your fluid pala, rather. Okay? So if you remember, right? If you remember back before, right, in here, right, we were talking about the kinds of sign conventions, right? So if you remember, there was the PV diagram right here, P, then V. Say for example, you have here a process that takes you from state 1 to state 2. Notice that if you're reading this from left to right, what is happening is that the volume is expanding, which means now that is work non-flow positive. On the other hand, you will make it work non-flow negative. That should also be the same for your P, or your work steady flow, right? It should be read top to bottom, right? And even though that registers as a negative in the integral, there's another negative sign at the back for it to be registered as positive. Notice that when your pressure decreases, right, just like what we said before, when your pressure decreases, you will see that your work steady flow is positive. And so, there you go. That is an expansion engine. Now we go to problem 5.4. This is the only problem for this one, so this will be somewhat simple. Steam enters a steady state turbine at a pressure and temperature of 30 bar, 360 degrees Celsius, leaving as a saturated vapor at 8 kPa. It is known that the turbine develops 8.95 megawatts and that the heat leaks out of the turbine at a rate of 0.586 megawatts. Neglecting kinetic and potential energy changes, the question is, how much steam was flowing into the turbine? Okay, it's very interesting. We will now have here problem 5.4, and we will have our given values. Right, given values. We will have here a turbine which has a state 1 and a state 2 as well. Okay? State 1 apparently is going to be 30 bar, 360 degrees Celsius, right? and leaves as a saturated vapor. This is now state 2, saturated vapor at 8 kPa. But again, we are working with steam. Steam tells us, I'm going to have to get from my property tables. So that means that I should turn this 8 kPa into bar, which is 0.08 bar. Okay? So if that is not yet somewhat semi-automatic or maybe automatic in your brain, I feel you may have to practice a little bit just so it doesn't bog you down. You don't have to write down the conversion factor for you to be able to convert very easily. Okay, so most probably I'm already thinking of a to-do list in here. The to-do list has us doing or has us trying to get the H1 and H2 values because that's what we need in the first place, right? It is known that the turbine develops, right? What that means is that it will generate power that is equivalent to, right? That is equivalent to 8.95 megawatts. And the thing about this is that I appreciate 8.95 megawatts, that is a ginormous number, but this is not something usable because what we use is in kilowatts. So 8.95 million is just 8,950,000, right? So 8,950 kilowatts. And then now notice as well, heat will leak out of the turbine at a rate of 0.586 megawatts. So now I'm using a curvy line to represent the heat loss because, well, right, that is when you're thinking of something that is hot, you do this, right? So that is my justification. That's going to be 0.58. What is this again? 586 megawatts. So instead of this, we will just put it as 586 kilowatts. And so now, anong gagawin? Right? Neglecting kinetic and potential energy changes, well, we can just do this thing again. We will now arrive at the situation wherein your negative W is H2 minus H1. We can just reuse this second law. But we can now no longer say that your Q is cancelled because very clearly there's a Q in here. There's a heat loss, right? This is going out, so this is heat going out, which means that this is actually negative negative 586. Right? Negative 586 minus your work is going out as well, 8,950. 8,950 is equal to your delta H. How are we going to compute for delta H? That will be m dot times H2 minus H1. And so as you can see, yeah, we just do need to find the values of H1 and H2. So for H2, that will just be HF because this is a saturated vapor. Yeah, saturated vapor. So sorry, it should be HG. HG at 0.08 bar, and it should be your H at, what was that again? 30 bar. And then 360 degrees Celsius. So let's try and find this now in our tables, right? We're here in the pressure table, might as well get 0.08, right? And that is at 2577.0. 2577.0 kilojoule per kilogram. This is from table A3. And then your H1 is going to be superheated vapor. We were given a pressure and a temperature. So we will get it from 30 bar 360. 30 bar 360, there you go. And our H is our third value in here, 3138.7. 3138.7 kilojoule per kilogram, which is from table A4. Now we just get everything. And notice, before we get this, before we go out, we should not let this slip away because how much steam is flowing into the turbine is not in kilograms per second. Usually, when we hear about how much steam, we think, okay, you know what, that's a mass flow rate. But no, it's a meter cube per second. So instead of this required being the mass flow rate, it is actually the volume flow rate flowing into the turbine. So now that is V/1, which if we think about it, is just m dash, not m dash, but m dot times v1. Oh, before we got, before we closed the table, right, we should remember that we should also get our value of v1, which is the v at the same thing that we were just looking at, 30 bar, 360 degrees Celsius, which in this case is the first value or the first number in here, which is 0.0923. 0.0923 meter cubed per kilogram. This is now from table A4 as well. And so, honestly, if you think about it, if you are very lazy, like I am, you can already get to the answer, which is your v/1. Your v/1, in this case, is m dot times v1. You already know the value of v1, and you can back solve for your m dot from here directly. How? By just substituting everything. Minus 586, right? Minus 8950, right? All of that is in kilowatts, by the way, all over your value of H2 minus H1. Your value of H2 is 2577.0 minus your H1 is 3138.7. 3138.7. Oh, sorry. 0.7. This is now kilojoule per kilogram. And then you will have in here V1, which is our, okay, you know what? I'm gonna have to move this a little bit. Here you go. Times 0.0923 meter cube per kilogram. Now notice that your kilowatts is just kilojoules per second, if you would like to think about it that way. And then divided by kilojoule per kilogram, cancel, you will get here, at the very least here, with a kilogram per second, which is indeed our value of m dot. So good job to us. That is our m dot, and this is our v1. Okay, so if we multiply this now with meter cube per kilogram, that will give us cancel. That will give us indeed a meter cube per second. And so we just put everything in our calculator. We will get a value of, let's see, negative 586, 8950, 2577.3138.7. We will get an answer of 0.0923. We will get a direct answer of 1.5670. 1.5670 meter cube per second. Oops. So that is your v/1. And that is how you're supposed to look at turbines. There's really not a lot to do here. If anything, this is one of the more involved problems for turbines. There's one especially interesting problem that I've given you guys for problem set 5, the one with the multiple stage reheating. The one with multiple stages. Number 7, right? Number 7. It's very interesting. Go ahead, try it out for yourself. Okay. And I suppose that's it, right? Because after this, we're done with turbines and expansion engines or turbines, right? And next, for part 5 of 7, we will have another little doozy, which is fluid movers, right? So I will see you then. See you on the next video. Thank you very much.